Hello, everyone. Welcome to the talk, Advancing GPU Analytics for Apache Spark with RAPIDS and Alluxio. My name is Adit Madan. I'm a product manager at Alluxio, where I've been for the last 5 years. I'm also a member of the project management committee of the Alluxio open source project. I'm very excited to present this talk with Dong from NVIDIA, without whom this collaboration wouldn't have been possible. For those of you who are not familiar with Alluxio, Alluxio is an open source project which came out of the same research lab at University of California, Berkeley as Apache Spark. There are 10 companies using Alluxio across different sectors, as you can see on the screen, especially technology, financial services, telecommunications and media, and also genomics and pharmaceuticals. Now, there are a few trends which justifies the whole premise for the talk today. When we look at the evolution of the big data ecosystem, we started with the co-location of compute and storage with one compute framework, which was Hadoop, and one storage system, which is HDFS. Since then, we've come a long way. And the first step in that journey was a disaggregated model in which compute and storage were not located on the same set of nodes. We've also transitioned from HDFS to new, cheaper, and modern object stores. And at the same time, there have been new compute frameworks which come into the picture, each which does a good job for a specific task. At the same time, there has been improvements in processor technology, including CPUs and GPUs. Now, when we look at the acceleration provided by GPUs specifically, now we've come a long way, and this speeds up the computation phase of an application. But at the same time, data access is a problem if not addressed. With the advancements in GPU computing, they drive a higher I/O traffic when compared to CPUs. And that's what we're going to focus on today, the data access path and how that affects an end-to-end compute job. Alluxio is a data orchestration system. It's a layer which sits between different compute frameworks and different storage systems. You can see different compute frameworks on the top of this picture, and you can see different storage systems at the bottom. Alluxio, as a layer which sits in the middle, manages movement of data across these different systems. Now, this movement itself could be access-based. For example, when a compute framework on the north accesses a storage system on the south, data is moved on demand from the storage system to the compute system, and only the data that was accessed is moved. At the same time, data movement can also be policy-based, where data is moved across storage systems based on policies such as access time. Modern data analytics or AI pipeline typically consists of a series of steps. This could be ingest, ETL, analytics, or model training. Now, different frameworks can also be used at the same time for different stages of the pipeline. Alluxio as a system sits between the compute, different stages, across different stages, and the storage systems. Now, when a Spark job in the ingest phase writes to Alluxio, the same data is cached in Alluxio and available for future stages in the data pipeline. Today, we're going to talk about a stack with NVIDIA GPUs for compute acceleration and Alluxio for I/O acceleration. The solution which we're going to talk about is applicable across different scenarios. As you can see on this picture, the two scenarios to keep in mind today is all-in cloud scenario, which is the picture on the left-hand side, which could be managed Hadoop or Kubernetes in a single cloud, Spark running on EC2 or similar cloud instances, and accessing storage, which could be in cloud object storage. Now, Alluxio is typically deployed on the same instances as Spark and as a separate process, which caches data and manages data when accessed across different storage systems, such as cloud object storages. But at the same time, the same solution is also valid on premises, where you have enterprise Hadoop or Kubernetes offerings with Spark and Alluxio accessing on-premise object stores, as you can see in the picture on the right-hand side. A few key takeaways from the talk today that I would like you to keep in mind. One is that Alluxio as a system unifies different data lakes. So you could think of if you have multiple different storage systems in a single cloud or across a private data center and a public cloud, Alluxio is a unifying layer which makes all data available, presented in a single unified namespace. The second thing is that Alluxio manages efficient representation of data and caching for fast data access. At the same time, the solution is applicable across different environments, as you'll see later in the talk. With that, I'll pass it on to Dong, who's going to talk about our integration, our collaboration with NVIDIA.
Thank you, Adit, for the great introduction. Now let me introduce myself a little bit. My name is Dong. I'm a solutions architect at NVIDIA. I specialize in accelerator performance tuning for machine learning, deep learning, and the data processing workflows. To give more information on RAPIDS Spark, so the RAPIDS Spark development is a joint community effort led by NVIDIA engineer team. So there are two major Spark features contributed. The first is as we know, Spark runs on various cluster scheduling environment, such as Yarn, Kubernetes, or standalones. We enable GPU support in all those schedulers so that Spark can discover, request, and assign accelerators using Spark APIs. And later on, in future, Spark also will be able to dynamically request GPU resources at a more granular level, like Spark stage level. Secondly, Spark 3 enable columnar processing. We extend Spark SQL Engine Catalyst, allow the SQL plugin integrated to be used on columnar format. This means the Spark node plan can actually exchange RDD of column batch instead of RDD of column Spark SQL rows. Through all those Spark 3 features, we brought the GPU acceleration to Spark, and we leverage the CUDA-X stack, which is the foundation of NVIDIA GPU software ecosystems. Currently in Spark, RAPIDS Spark accelerate Spark SQL with Spark DataFrame APIs. We also accelerate machine learning libraries such as XGBoost and deep learning libraries. So all those changes to enable accelerations is minimum. So we build all those acceleration on two pillars. The first is RAPIDS. The second is UCX. So looking at the Spark, there are really two things we want to accelerate, and they are interleaved. It's Spark SQL and Spark Shuffle. First of all, RAPIDS Spark SQL plugin is what we use to accelerate Spark SQL. It is implemented with cuDF. cuDF is an open source library that use error-based data in GPU format. So our Spark developers create the Java API on top of cuDF to be leveraged by Spark. So with RAPIDS Spark SQL plugin, we provide transparent drop-in replacement. The user only make change to configurations. We know that in a Spark SQL workflow, first we need to convert the SQL query to a logical plan and apply some sort of optimization like filter push down, then convert the logical plan to physical plan and compare the physical plans through a cost-based model. Then goes to the code-gen phases to generate the diag of RDDs. So our optimizations happens before code gens. So before code gen, we provide the drop-in replacement of GPU operators over CPU operators, so that we keep all the logical plan level optimizations. And for the newer Spark release, we also work really well with newer features like AQEs in Spark. For Spark Shuffle, we leverage a library called UCX. As known by many Spark developers, Shuffle is the biggest challenges to use Spark. With UCX, we can combine the Shuffle data into larger chunks and also enable GPU-centric data movement over network, storage, and the GPU systems. So how do we experiment with RAPIDS Spark? Right? RAPIDS Spark is available in all clouds. First of all, in EMR, we ship with every EMR released after 6.1. We also provide bootstrap scripts for Google Databricks and the Databricks. So in all those environments, we also work with other vendors like Cloudera to provide the support in various enterprise environments. In either of those environments, it's very easy to allocate scale out T4 GPUs. It's really the price is really good, so it's very economic and easy to spin up a RAPIDS Spark cluster to give it a try yourself. Now, with all the acceleration we mentioned, the Spark SQL queries that used to be compute bound is now I/O bound. So we observe that storage and the network are often become a bottleneck, and especially with modern cloud enterprise data architectures, there are multi-cloud, hybrid cloud. So this led us to think of we can leverage data caching orchestration system to help the performance, and that's where Alluxio step in. We work with Alluxio team closely. I just want to give a shout out to Adit Madan and David Zhu for their help to make this possible. Alluxio and Spark are really easy to use together. As we can see, right, for existing Alluxio users, we can just install the RAPIDS Spark plugin and point the Spark SQL to the existing Alluxio files. For existing Spark users, after deploy Spark RAPIDS, we also provide a configuration in Spark RAPIDS to map a storage to a Alluxio namespace, so that in either way the user can combine the Alluxio with RAPIDS Spark easily. So to show the benefits, we run a set of benchmark in cloud environment. Here we chose Google Databricks because we have init script to make it really flexible to deploy and configure Alluxio with RAPIDS Spark. We can say that GPU nodes cost more than CPUs, but because our GPU software is so much faster, the query runtime cost is actually much lower. And also in a typical analytical workflow, such as machine learning or AI pipelines, it's often a sequence of steps that happens iteratively on the same set of data. So that's why we think the Alluxio can really help to boost up the performance. Here we use a set of standard SQL query that we call NVIDIA decision support queries to do this benchmark. So to apply both RAPIDS Spark GPU and Alluxio, we run about 90 SQL queries on 3 terabytes of CSV data on multiple tables, and compress them to 1 terabyte of Parquet files. And this chart shows that with the GPU cluster and also with Alluxio deployment, we provide nearly 2x of improvement in performance when compared the total times across the 90 queries, and 70% better return on investment compared with the CPU cluster. We want to note that not every query is GPU friendly. Those are just common query that you might be using, but we see a great overall speed up. So we want to use that to demonstrate benefits. So to make the best use of Alluxio and RAPIDS Spark, we recommend the user to look into a few configurations. First of all, we want the user to co-locate Alluxio workers with Spark GPU workers So this enables the application to perform short-circuit reads and writes with local Alluxio workers, which is more efficient than remote. And also, it's very important to allocate enough space to Alluxio cache. In fact, it's recommended to have enough cache space for multiple copies. And also, user can choose between memory and SSDs as the cache medium for their Alluxio workers. Unless the data is small enough to fit in your system memory, it's often beneficial to deploy more economical SSDs as the caching layers. It also improves the TCO. On the RAPIDS Spark side, first of all, the Spark.rapids.sql.enable is the main switch to turn on and off the GPU accelerations. And also, when as a user, when we debug the queries, it's very useful to use spark.rapids.sql.explain. So when we set it to not on GPU, it only print out the incompatible ops that cannot be run on GPUs. Because the bottleneck when you use a RAPIDS plugin is that often we see that the operators in Spark queries hops between CPU and the GPU, so there's a lot of data movement. We want to avoid that. And also, there are some common basic configurations, such as the concurrencies. As we know, the concurrencies in Spark is controlled by the number of tasks per executors. With RAPIDS for Spark, we introduce an additional parameter called rapids.sql.concurrent GPU task. With this, we can further control the GPU task concurrency and to avoid the out-of-memory exceptions given the limited GPU memories. Some of the queries significantly benefits when setting this to a value between 2 and 4, and typically 2 provides most benefits. And it's also beneficial to have a higher number of tasks, for example 4, with, for example, 2 concurrent GPU tasks, so that we can offset the I/O and the compute. For example, one task might be communicating with the distributed file system to fetch in an input buffer, and it is not actually doing a lot of compute, but the other task can be decoding an input buffer on the GPU, which is actually compute heavy. So that we kind of always have some tasks doing I/O, some tasks doing compute, which is good for performance. However, when you configure too many concurrent tasks, it might lead to excessive I/O and overload the host memory. So we typically find that 2 times of the number of concurrent GPU tasks is a good number to set for the tasks per executors. And also setting spark.rapids.memory.pin pool size also helps, because it improves the performance of data transfer between the GPU and the CPU memory, as the transfer can be performed asynchronously from the CPUs. Ideally, the amount of pin memory allocated would be sufficient to hold input partition for the number of concurrent tasks, so that Spark can schedule for the executors. Okay, I'm gonna hand it back to Adit, and he will talk more about exciting new features in Alluxio.
Thanks, Dong, for the great section. Next, I'm going to talk about some core features in Alluxio which enable the solution that we just talked about. Alluxio is, like I said, a data orchestration layer, which is accessed using different interfaces. So with a system like Spark, it typically accesses Alluxio using the HDFS-compatible API, which enables no application changes when using Alluxio and RAPIDS. Now, Alluxio as a layer in the middle talks to different storage systems using different drivers, which you can see on the bottom side of this picture. Now, I'm talking to GCS or S3. We use the S3 driver, for example, to talk to Amazon S3. And in the case of GCS, we also have a driver to talk to Google Cloud Storage. New machine learning applications or PyTorch applications, they talk to Alluxio using a POSIX interface, And that's also the interface that TensorFlow uses to talk to Alluxio. Now, the beauty of having multiple different APIs is that Alluxio enables a global data platform for various different applications which may be present in your data platform itself. One key thing to mention here is that multiple different storage systems, they are presented to the application in the same file system namespace. The way this works with Alluxio is that different storage systems are mounted to a particular section of the Alluxio file system namespace. As you can see in this picture, Alluxio, the root of the Alluxio file system is pointing to an HDFS location on the right-hand side. But at the same time, a directory called data is backed by two storage systems at the same time. Data, as you can see, that it has subdirectories called reports and sales. And these two subdirectories are present in HDFS, but also S3 at the same time. This powerful feature enables features in Alluxio for policy-based migration in which data can be moved across different storage systems without any interruptions to the applications. From a performance standpoint, in the solution that Dong mentioned, the reason why we see higher performance with Alluxio in the mix is that Alluxio manages certain tier storage, local storage, on the nodes on which Spark is running. So we would typically carve out, for example, SSD resources on the nodes in which Spark is running for Alluxio to manage. And Alluxio manages this local storage for caching data which is remote. So in the case of Google Cloud Storage, any data which is accessed and is hot is managed in Alluxio cache transparently to the application. This intelligent multi-tiering ensures that we see performance benefits for data when it's cached and data is evicted at the same time, which is not being used anymore. At the same time, Alluxio caches metadata with consistency. So when you access a file in GCS using Alluxio, Alluxio would cache the metadata in the Alluxio file system master. Alluxio has a master worker architecture in which master is responsible for the metadata and the workers are responsible for caching the data itself. Now, the cache in Alluxio is consistent. So if you make any changes to the file system, such as a mutation on file 1, as you can see in this picture, that those changes are reflected on the Alluxio file system master. Now, data operations can be synchronous or asynchronous. Synchronous data operations are when you write to Alluxio and you also want the rights to propagate to the underlying storage system. In the case of reading, which is the case in the joint solution that we presented today, caching actually happens asynchronously. So when you read a data, the data is read the data for the first time. We return to the client that the read request is a success, but we also cache the same data asynchronously in the background, reading from the underlying storage system, such as GCS, into Alluxio managed storage. Now, the same is possible for writes, and you can trigger this loading of data from GCS into Alluxio namespace by using a tool in Alluxio called distributed load. Now, the purpose of a tool like distributed load is that you can preload the data by specific triggers so that the first access of data doesn't take a performance hit. This is true for both reads and writes. A few key takeaways from this talk, just to reiterate them. One is that Alluxio as a system unifies different data lakes without any application changes. In the solution that we presented, GPU applications with Spark can be migrated to using GPUs and Alluxio without any application changes. Data locality by Alluxio managing storage close to the compute on the same instances as the compute makes sure that you have the benefits of data locality and associated performance. Now, the benefit of performance in this case, as we saw, was that we saw 2x performance acceleration with Alluxio in the mix. And at the same time, with GPUs and Alluxio, we saw a higher ROI compared to CPUs. The solution with both RAPIDS and Alluxio is applicable to multiple environments across different cloud providers or on-premises environments, either bare metal or Kubernetes. Here are a few references in case you want to learn more about the solution. We have a joint blog with NVIDIA talking about the presentation today. We also have a getting started documentation for RAPIDS and Alluxio together. We have documentation for RAPIDS itself and Alluxio, different work on top of Alluxio. Thank you a lot for joining the talk today.